Hello, in this lesson we're going to solve two problems related to friction forces. Okay, so for problem number 1, we want to show that the acceleration of any object down an incline where friction behaves simply, that is, we have the regular friction formula. This acceleration is g times the sine of the angle minus the friction coefficient times the cosine of this angle. Alright, so here we have our system. We have this object in a ramp of this that has an angle, and these are the forces acting on our system. We have the weight of the block here with the two components, x and y component, taking the plane, the ramp as a reference, okay? The normal force to balance with this y component of the weight, and the friction force in the opposite direction, okay? So in the end, this block will be going down, so we have a net force that's actually the x component of the weight minus the friction force. We know that the friction force can be calculated by the friction coefficient, in this case the kinetic coefficient, okay, it's moving, the block is going to be moving, times the normal force. In this case here, the normal force is the same as the weight in the y direction, okay? So we have the coefficient times mass times the gravity and the acceleration of gravity times the cosine of this angle here, okay? Now for the weight in the x component of the weight, we have mg sine of this angle, all right? Now we can just insert this in our first formula, all right? This is the equilibrium for the in the x direction. So we can just add both equations. We know that the force, the external net force, is actually mass times acceleration. We can just isolate mass here, isolate the acceleration, cut the masses, and we have the formula that we wanted to demonstrate. Okay, let's go through problem number 2 now. So in this situation here, there's someone, a contestant in a winter sporting, that's pushing a 45 kilogram block of ice across a frozen lake. Okay, we want to calculate the minimum force he must exert on the block moving, exert on the block for it to start moving, and what is the magnitude of its acceleration once it starts to move, and if that force is maintained, okay? So if he maintains the same amount of force, what is the magnitude of its acceleration? Alright, let's do the balance. I forgot. We have the coefficients, the friction coefficients for ice on ice. We have an ice cube, ice block on a frozen lake. So the coefficients for ice on ice are this one, the kinetic coefficient and the static coefficient, okay? So these are the forces we have in our system. We have this force here of the person that's acting on the block. We can decompose it into x and y directions. We have the weight of the block, the normal force, and the friction force in the opposite direction of the movement. Okay, so for letter A, in order for it to start moving, we can just do the balance for the x and y directions, okay? So in the x direction, until now, nothing is moving, right? He's making a force here, but it's still not moving. So we can make the F in the x component equals to the friction force, all right? In this case, remember, it's not moving yet, so you're using the static coefficient, friction coefficient, okay? And here we have equation number 1. The force times the cosine of the angle equals the friction coefficient times the normal force. Alright, in the y direction, we have that this normal force is actually the force in the y component of the force plus the weight of the block. So in this case, we know that the y component is f sine of the angle, and the weight is mg. And here we have equation number 2. Now we have a system with two equations, alright? In this case here, we can just add equation number 2 in 1. So now we put everything in terms of f. For this case here, I'm just adding, instead of the normal force here, I'm adding this expression, okay? So in this case here, I'm just adding the values, and well, I can isolate the normal the force itself. I just multiplying here, opening the equation, and we can isolate the force that the person is applying on the block, okay? Now we know everything here. We know the angle, the friction coefficient, the mass, and the acceleration of gravity. Add the numbers, and we have the force that's approximately 51 newtons. Okay, now for letter B, what is the magnitude of its acceleration when it starts to move if that force is maintained? Okay, now we know we're dealing with kinetic friction coefficient, right? Because it starts to move. And when it starts to move, we have now in the x direction net for external force, and it would be the force in the x component of the force minus the friction force. And in this case here, we already know that's the friction force formula, but we have to recalculate it for the kinetic friction coefficient, okay? From equation, and we also don't know yet the normal force, but from equation number 2, now that we know the force that we apply, we can use the equation to calculate the normal force, okay? Now, using the kinetic coefficient and the normal force, we find the friction force when the block starts to move, okay? We know that the f in the x component is f cosine of the angle minus this friction force we just calculated. We also know that the f equals m, that's 45 kilograms, times the acceleration. And now we can just isolate the acceleration and find that it's 0.7 meters per second squared.
Physics can be easy. Subscribe to our channel and learn with the geeks.